Today we study C23 Harmonic Oscillator and Harmonic Law. So you can download the PDF file of this lecture. You first visit the kpop.org. It's our digital library with the K-pop collaboration. If you scroll down, you can find the table of contents. Escape from Scientific Absurdity C series. Click this. If you scroll down, you will reach the C23 Harmonic Oscillator and Harmonic Law. If you click this, you'll find this PDF file. After this class, I will upload this PDF, this video file to YouTube, and you can click this button next to E, and if you click this, you can return to our digital library. Okay, and then if you have not subscribed this K-pop YouTube channel, you can subscribe by clicking this button. Okay, let's begin with the C23 Harmonic Oscillator and Harmonic Law. The first part of this lecture will be regarding the solution of the harmonic oscillator. We are now very familiar with because we have studied in detail about the second order differential equation that are given before. For example, if you go there, we have studied a second series. We have studied various algebraic tools and calculus to attack this problem. And actually in the series A and B, further details of tools to find the solutions of the differential equation for the equation of motion for the harmonic oscillator. So let me briefly explain how to find the solution for the harmonic oscillator first, and then we attack the problem of Kepler's third law. The harmonic oscillator equation of motion comes from Newton's second law. Hence, Newton's second law states that this is mass times acceleration. And if the mass is applied by the restoring force, that is opposite to the displaced from the equilibrium position. And if it is restricted to the one-dimensional motion, then we can construct this equation in one dimension. We know we can simplify this equation by rescaling it into the differential equation of number. We know x is of dimensions of length, and the harmonic oscillator is restricted to move between 2 points we call amplitude, and we have equilibrium position, and the maximum reach is this, and the other direction we have minus a. So they are equal and is oscillating repeatedly. So we introduce a parameter A that is called the amplitude of this oscillation, and we rescale the coordinate x for the displacement from the equilibrium position scaled by A. That is a kind of unit of length. Then this C becomes restricted to the region -1 to +1 because x is in between -a and +a, and we divide them by a. Okay, and then we divide the equation because we have a factor of a out, and c double time derivative kc equals 0. I can divide this equation by a that is non-zero. And then we divide this equation by k, then our equation reduces it into a dimensionless case. Here we define this one can be expressed as d squared and something square, and that is a square root k over mt. We define this one by tau that is dimensionless. So this one can be defined as the derivative, double time derivative, a scaleless time derivative with respect to tau, and that is dimensionless. It is apparent that this operator, second order derivative operator, proportional to the second order time derivative, is dimensionless because it is added, this whole thing is added to 1. That is dimensionless. As a result, this coefficient, this parameter, has the dimension of time to cancel the dimensions of time in here. So this tau is dimensionless, and this c is dimensionless too. We have reached the point, this one is a double tau derivative plus c equals 0. Don't forget the conversion rule from c and tau to x and time t. So we'd like to know the answer. What is the general solution of this dimensionless differential equation originating from harmonic oscillator? You can follow this to reach the point that you can try the solution, a linear combination of a sine and cosine, whose argument is a dimensionless parameter tau. And if you take the derivative, this trial solution, you have a single derivative of flips the sine and flips the cosine into sine and sine into cosine. If you take the derivative one more time to have the double time derivative, okay, let's see. I made a mistake. This should be our original equation of a double tau derivative, and so it should be replaced with double tau derivative instead of a time derivative. Sorry about it. Let me correct it immediately. Okay, I have corrected that part. So in here, this double dot and single dot for c represent the derivative with respect to tau instead of time. So it is the derivative with respect to tau. If I take the first order tau derivative, this trial solution becomes minus, cosine becomes minus sine, and sine becomes cosine. So if I take another tau derivative, we have sine becomes cosine, so we have over a negative sign. Cosine becomes a minus sign. So both the cosine term and sine term becomes minus. Therefore, if I move this one to the left-hand side, I find that this trial solution satisfies the equation of motion. Let's see, we have this linear combination, and we have developed a way to find out the relation by integration in problem B. And we make use of this the result of C to find the result of C can be converted into this kind of form. The second order, the double integral of this trial solution will lead to this part. And actually, if I make use of this trial solution, it returns to the same form. Okay, so if you substitute the cosine and sine of the linear combination with the arbitrary constant C1 and C2, you will find that if you substitute the 0 in here, this is C0, cosine 0 is 1, and plus C0 prime, sine 0 is 0. Okay. This C0 is nothing but the initial position. C0 is C evaluate 0. And if I take the first order time derivative, tau derivative, it becomes minus C0 sine tau plus C0 dot cosine tau. So if I substitute 0, C dot 0 equals this guy vanishes and only this one survives. So this one is the initial velocity in the dimensionless variable C. So using this, we return to the original problem. This one has a solution, this. So this is the solution. However, now we convert C and tau in terms of the physical variable x and time t. So the result is this. Let's substitute the 0, x0 cosine square root k over m 0. What's that? The next term is x0 dot m over k sine k over m 0. So this one vanishes. This one is a 1. Aha. This coefficient represents the initial position. x0 is x evaluate time equals 0. What is the velocity? X dot t in general is x0. Cosine becomes a sine minus, and we have k over m sine k over mt. Take the derivative. You have sine becomes cosine. But if I have this one differentiated, this factor cancels and it becomes cosine. If I substitute 0, this sine 0 vanishes and this coefficient becomes reduced into this simple form, and cosine 0 is 1. Okay, so x0 dot is x dot evaluated at t equals 0. So this is the exact solution for the harmonic oscillator when the initial value for the position and the velocity are given like this. Next, we consider Kepler's law. We remember in the previous class, the orbit of a planet can be expressed in terms of relative coordinate, that is the magnitude of the displacement, relative displacement. This is sun and this is planet. Okay, so, and the angle theta is the polar angle defined in the 2-dimension. If you have the bound or kind of bound state like the planet in a solar system, the energy, total mechanical energy of the system is negative. In that case, it becomes a bound state, and lowest possible state is a circular orbit, and then we have an orbit that is an ellipse. And it is parameterized by this expression, where epsilon is the eccentricity that is between 0 and 1. When epsilon equals 0, this equation tells us that radius is fixed to the alpha, that is called the semi-latus rectum. So circular orbit's radius is alpha. And then if epsilon is between 0 and 1, this one varies. Because of this, radius is alpha over 1 plus epsilon cosine theta. It ranges, cosine theta ranges from -1 to +1. So we have a various value of radius. And we have minimum at cosine theta equals 0. We have maximum value of the radius. This radius is the magnitude of the relative coordinate, the distance between the sun and planet, and the maximum value is alpha over 1 minus epsilon. Minimum value is alpha over 1 plus epsilon, something like that. In fact, our system has a center of mass here, and relative coordinate is this. So at the center of mass frame, that is inertial reference frame, R is defined by this. However, mathematically, it's better to draw this rather than this. It is rather complicated. So we convert this one to a non-inertial reference frame. This is a CM, and actually the CM is somewhere around here. At the focus, the sun is shifted to the focus, and planet is shifted to the point. So this plot is mathematically useful. However, this plot is not drawn in an inertial reference frame. It is not an inertial reference frame. So we should be very careful distinguishing the two frames. It is a non-inertial reference frame. it reaches the inertial reference frame only if the mass of the sun is infinity. So the mass of the planet, if the mass of the planet is negligible, you can treat this one as an inertial reference frame. But in fact, sun is much heavier than the Earth. This error won't be very large if you even treat this diagram to be drawn in an inertial reference frame, although it is not an inertial reference frame. Okay, if you draw this one by choosing a center that is unphysical and choosing the focus that is this point, okay, and this one is fixed, so this is the relative coordinate system. So this is the inertial, non-inertial reference frame at which the sun is fixed to the focus of this plot. Okay, from then on, everything else is straightforward. According to geometry, you can draw right triangles, and first of all, the distance from the satellite to the sun varies from minimum value to maximum value. So we call this the sum of the R minimum and R maximum, twice of A, where A is called the semi means half. This is 2A, so half of 2A is A. That A is sum of R max and R min divided by 2. So that is A, semi-major axis A. We recall that this formula states that the R minimum is alpha divided by 1 plus epsilon. R maximum is alpha divided by 1 minus epsilon. If I add them up, the result is this. So we have a correlation among the semi-latus rectum alpha, that is the radius of the orbit when it is a circle. And circle represent the case epsilon equals 0. Eccentricity becomes 0 when it is a circle. In addition, we have a geometry to find a relationship among them. Okay. So we have a correlation among semi-major axis and semi-minor axis. Semi-minor axis is the half of this height. So this is B, semi-minor axis. Semi-minor axis, semi-major axis, and focus. This is a focus. Focus has the formula epsilon A is the focus. So if epsilon equals 0, this focus approaches the origin. That is the case for a circular orbit. Because of this right triangle, I have this kind of correlation among semi-major axis, semi-minor axis, focus, and eccentricity. So a little bit busy because we are dealing with many variables. They are all correlated. So in summary, we find these correlation to be simplified like that. Why don't we introduce a coordinate system at which these coordinates are x, y, Cartesian coordinates, whose origin is not the focus, but this. A little bit tedious computation shows that the Cartesian coordinates of x and y are expressed like that. If you sum x squared over a squared, we will find x over a from this and y over b from this. And if you sum them all, you will find this expression. A little bit busy, but it is exactly equal to unity. So we call this one to be the equation for an ellipse. Next, we consider how to compute the area of an ellipse. It is trivial if you make use of the fact that a unit circle have the area pi 1 square, that is pi. And actually, if you change the variable from x and y to c and eta, you will find the area of this ellipse can be scaled with a times b multiplied by an area of a unit circle. So this rescaling is a very, very useful, and we don't have to evaluate complicated integral. But in principle, you can do that. Finally, the area of an ellipse of semi-major axis A and semi-minor axis B to be pi AB. Now, finally, we apply this idea to derive the Kepler's third law directly from the equation of motion developed by Newton. Newton's second law, in association with Newton's universal gravity, produced this very simple equation. We call it equals to 0 for the is identical to the harmonic oscillator, and we have additional piece that is a constant 1 over alpha. We remember this variable u is nothing but the 1 over r, where r is the relative coordinate vector, that is relative magnitude of the relative displacement from the sun to the earth, or vice versa. So relative distance of the sun and a planet. Okay, so we remember that alpha is the semi-lattice rectum that is completely determined by the orbital angular momentum, masses of the planet, sun, and the gravitational constant. Find out the general solution of this equation. This is identical to harmonic oscillator. Harmonic oscillator. The solution of a harmonic oscillator, except that we have additional constant term. But this constant term can be obtained by a trivial way. If you substitute 1 over alpha, then you have a solution. U equals 1 over alpha is a solution of this differential equation. Why? If I have a constant alpha, this second order derivative with respect to angle vanishes completely, and it is identical to the right hand side. But that is not the general solution. We say it is a particular solution to u. The general solution is sum of this particular solution and something that is the solution for the homogeneous equation, that is second the derivative of u with respect to angle and plus u equals 0. We know the answer. That is the linear combination of cosine and sine. We know that the two sine and cosine of the same period can always be unified into a single sinusoidal function up to an overall factor called amplitude. We scale 1 over alpha out, then the expression becomes compact and we defined the amplitude by epsilon, and that is identified in geometry to be the eccentricity of conic section. Finally, the general solution is completely obtained in this form, and that is identical to what we listed before. Okay, so as a result, we make use of this conic section trajectory, describe the shape of the orbit, epsilon equals 0. The solution is r equals alpha, and we know what alpha is. It is completely determined by the orbital angular momentum. Derive the harmonic law of Kepler's planetary motion. Kepler's second law states that orbital angular momentum. Sure, Kepler didn't know what the orbital angular momentum is, but he stated that the area of velocity is preserved. The Newton's second law, and the rotational version of the Newton's second law, states that any central force, any two-body system, many-body system, under no external force, except that the two objects are connected, communicate with each other via gravitational force that is conservative and central, the angular momentum is conserved. And we recall that this angular momentum is a reduced mass multiplied by the relative coordinate vector squared multiplied by the angular velocity, theta dot, from which we can find the relationship of the differential of time and differential of angle. We know mu, reduced mass, and orbital angular momentum are both conserved. We factor out this conserved quantity and find that r squared d theta. This is related to the twice of the area of the orbit. We recall that this is not evaluation in polar coordinates. It's not simple. However, its evaluation can be made by making use of the rescaling method that we just have obtained. Therefore, the area of an ellipse with the semi-major axis A and semi-minor axis B is found to be like that. We remember the area of this orbit can also be obtained by explicit computation. If you learn the calculus course, or if you are able to study the complex variable, then you can make use of the contour integral to find it very simply. Anyway, note that the area can be expressed in terms of the different parameters, including semi-latus rectilineae and eccentricity, and so on. Finally, eventually, because of these relations, we find that the period squared is eventually expressed as this constant multiplied by the cube of the semi-major axis. Newton was able to find this relationship, and his constant of universal gravity and the sum of the two masses and over a factor coming from the area of an ellipse. Okay, so including this result, he found a lot of things, and it was published as a Principia. And he was not the person who published. The person, young guy, Edmund Halley, he was rich, and he used up all his money, almost all his money, to publish the Newton's Principia. He even persuaded him to let it published. And by himself, Edmund Halley was able to reproduce the result for the circular orbit with the eccentricity is 0. Why don't we read it through? There's a very interesting paper in it. Okay, that's it for today. Thank you.